So now we're going to leave behind the topics in trigonometry and move on to some topics in algebra. And in this chapter, we're only going to cover two sections. Both of them deal with the conic sections. So the conic sections are the shapes that you pick up when you slice a cone in certain ways. So I'm going to use a picture from a textbook because I don't have a picture of this in the notes, and I can't possibly draw this. I'm not that talented. So if you look here at this, these first three shapes you can get from just one cone. The fourth one you need two cones to get the shape. So if you slice perpendicular to the axis of the cone, you'll pick up a circle. If you're at an angle, you'll pick up what's called an ellipse, but not going through the base of the cone. And here, if you go through the base of the cone at an angle, you pick up a parabola. And if you slice parallel to the axis of the cone, you get, well, half of a hyperbola. So if you put two cones tip to tip, then you get two sections here. These are called the branches of the hyperbola. So the hyperbola is made up of two parts that aren't connected. All right, so the ellipse, we're going to start with the ellipse. I should say the circle is a conic section, but you should have worked with circles in college algebra, so we aren't going to work with those here. We're just going to focus on the ellipse, the parabola, and the hyperbola. Now the parabola, you might be thinking, well, I've worked with that as well, which is true, but we kind of give it a different treatment with the conic section treatment, so a little bit different focus there. All right, so let's start with the ellipse. The ellipse is the set of all points in a plane in which the sum of the distances from two fixed points f1 and f2 is constant. So if you could imagine like a string, I already have the ellipse here, but you take 2 points and then connect a string of a certain length, a fixed length, I should say. And you say you pull the string with your pencil and go around. The shape that you'll pick up is an ellipse. So this distance and this distance is constant. So if you can imagine, you take any point on the ellipse, these lengths would add up to the same number every time, right? No matter where you're going from. So these 2 points are called each one is called a focus. Plural of focus is foci. So these are the foci. I'll use F to represent those. So this is F1 and F2, excuse me. So foci, plural of focus. All right, so the equation for an ellipse centered at the origin. We're going to start in this section. Everything is centered at the origin, and then we'll talk about shifting that in the next section. So an ellipse centered at the origin, the equation would look like one of these two equations. And in these equations, notice in standard form, this is called standard form, or standard equation, right? The standard form of the equation. You can write it in different ways, but this standard form would have a 1 isolated on one side. The x squared term would be first, and the y squared term would be second. And here, this a squared here, whatever that number is, should be bigger than the number here, b squared. Now these can actually have, the number under y squared can be bigger, but then we're going to call it a instead. So we want to notice which one is bigger. And whatever number is bigger, that's the one we're going to refer to as the a squared. So a squared has to be bigger than b squared here. So when we do this, set it up this way, then the major axis, and the major axis is the long axis. So this is the major axis, this is the minor axis of this ellipse, and so we would say the major axis here is vertical, whereas here the major axis is horizontal, right? Let me write that down. So you determine which way the major axis runs by where this larger number is. So if the larger number is paired with the x squared term, the major axis is actually horizontal. So I probably should have flipped these around. This one goes here. And this one goes here. And don't worry too much about what's A and B. It's more like which one is the bigger number, right? That's what you want to focus on. So whichever one is bigger, if this is bigger, then the major axis runs parallel to the y-axis. And if this number down under x squared is bigger, then the major axis runs parallel to the x-axis. So the length of this major axis is 2a. So let me write that here too. So whatever this number is here, you take the square root of it to find a, and this is twice that number. So you, from the origin, you just go up that many units, down that many units, or left and right that many units. These are called the vertices then. I'll just label them V1 and V2. And you can find two other points on the ellipse by using b. So b squared, take the square root, you get b. This would be b, and this would be negative b. So this is what we call the minor axis, and has a length of 2b then, twice of whatever b is. Whoops, why did I put a negative 2? That was supposed to be a b. Weird. Suppose I saw that too. Okay. I do weird things like that. Alright, so here this is 2b. So, but these points are not called vertices, even though they are points on the ellipse. The vertices are on the major axis. And then we can find the foci using this equation. Take the larger of the numbers minus the smaller, and this, whatever these numbers are, so not the square roots, but actually the numbers here. Find the difference, and c squared is that difference. Then you can take the square root to find c, and c is the number of units the foci lie from the center on the major axis. So these are centered at the origin, so the center will be the origin. Later when we shift that, it's just from the center of the ellipse. It doesn't have to be from 0, 0. So the foci are always on the major axis. And this length here is c. I'll put here, because I should have went the other way there, but you get the idea, right? C. Here. Here, I'll move that. So of course the distance between the two foci is 2c. Okay. Oops, on this side. Once you get used to the relationships, do a couple examples, it's pretty easy. So you just look at these numbers here. This one's bigger, so the major axis runs parallel to the x-axis, and a lot of times these are perfect squares, but if they're not, you can approximate. The square root of 16 is 4, so you just count 4 units in either direction from the center. Now the center is the origin here. Later that center might be somewhere else, so you just count from the center. So plus 4 minus 4. And then, so in other words, a squared is 16, which implies a equals 4. And then b squared is 9, which implies b equals 3. those will be the other 2 points on the ellipse that we can find easily. Now, when it says to find the foci and the vertices, these are the vertices, right? So 4, 0, and negative 4, 0. If you want, you can write for short plus or minus 4, 0, which represent the points. Then the foci, well, here, before I do that, let me complete my graph. So you just, do the best you can to make this look elliptical. There we go. When I grade something like this, I'm going to be looking that you have these 4 points in the correct spot. If that's not the best ellipse, that's fine. Foci, so here we need to use the fact that c squared is a squared minus b squared. So you always subtract bigger minus smaller. So 16 minus 9. These are already squared here, so you just plug these numbers in. And of course that's 7, which would imply that c is the square root of 7. So since this is centered at 0, 0, that's easy. You're just adding and subtracting square root of 7 from 0. If we wanted to label those on the graph, square root of 7 is approximately 2.6. So put them about here and here. And for the labeling, if you want, you can just write F1, F2. You don't have to put the coordinates there. And of course, this is V1, V2. Excuse me. Okay, so this one was already in standard form. It's really easy just to pick everything out. Now, if it's not in standard form like this one, what we need to do is you always want to get this 1 here, so you're going to take this number and divide everything by that number. So divide both sides by 324. And of course 324 over 324 is 1. And (36) times 9 is 324. So these cancel. You get x squared over 9 plus y squared over 36 equals 1. So this is bigger, so that means the major axis runs alongside of y, parallel to the y-axis. And I'm saying, it's actually on the y-axis, but once the center shifts, right, that's not always the case. So that's why I just think of it as parallel to y, because it can go somewhere else later. All right, so up 6, down 6, those are the vertices. Once these things shift, you're going to have to write 2 separate points. But when it's centered at the origin, you can take the shortcut there. Whoops, and I messed up, didn't I? Because this would be these points. I want to switch those around. X is 0 this time. Y is plus or minus 6. All right, and then the foci. Actually, I'll finish the graph first. So plus or minus 6, and then square root of 9 is 3. So plus or minus 3 for the minor axis. And we got those points. And then here's our ellipse. And for the foci, whoops, of course 0, we need to find the y coordinates. C squared would equal 36 minus 9, which is 27. So C is the square root of 27, which is 3 radical 3. And so plus or minus 3 radical 3. Again, if I ask you to label, I didn't say that in this, but a lot of times I do that on tests. I say to label them. So you just need to plot those points. 3 radical 3 is about 5.2. So there's one focus and there's the other. And then V1, V2. The more elongated your ellipse is, the farther away the foci are from the center. The closer those are to the center of the ellipse, the more circular it becomes. And then, in fact, if those 2 points meet in the center, it becomes a circle. Okay, so those are ellipses centered at the origin. Centered at the origin is pretty straightforward.